Greetings, everybody! Hey, we're here to talk about star death. Sounds like a real cheery subject, I know, but believe it or not, star death is important in the history of the universe because it leads to Earth-like planets, how about that, and complex forms of life. So you can't sneeze at that. This is a big deal. And what I've got on the screen right here is this is Betelgeuse, a famous star. It's in Orion. Here's the little Orion chart with Rigel and the belt, and up here on the upper left, Betelgeuse. If you've ever seen Orion, you've seen Betelgeuse. This is a star that's getting ready to go supernova. And it's about 20 solar masses, give or take. Notice this is an actual image of Betelgeuse. It doesn't look very round, and people were thinking, man, it's fading away and it's got a weird shape. That may mean it's going to blow up, but the chances are it won't blow up for a long time. People are saying roughly in the next 100,000 years it may go supernova, or it could happen tonight. So you just don't know. It's about 640 light years away. So the nice thing is when it does blow up, we will not be killed. We'll be able to enjoy the show. It'll look like the full moon in the sky during the day for a few weeks. It'll be quite a show. If you wonder why it's not round, it's because they're speculating that the Betelgeuse is throwing out some dark material that's covering up portions of the actual round image. And that's a speculation, but it's really possible. Okay, so supernovas are when a star runs out of its nuclear fuel and then blows up. And we'll talk about why that happens a little bit more. But they occur in all galaxies, and I threw this photo in here. This is M82. It's a galaxy. There's the galaxy right there. And here is, they're pointing out a supernova in the galaxy. Supernovas are so bright that they often outshine their own galaxies, okay? And remember, 8 is the magic number. You have to be greater than 8 times the mass of the sun if you want to be a supernova. Now, not all supernovas are far away. This is the Crab Nebula, probably the most famous supernova remnant. This is the result of a supernova in 1054 AD. It was actually observed, but I'm laughing because the people in 1054 AD did not know about supernovas. They didn't even know what stars were. They didn't even know what planets were. So they were, to them it was a big explosion in the sky, But anyway, this is this thing has, in the center of it, it has a pulsar, okay? And the pulsar is it's big, it's about 30 kilometers across, and it is pulsating at about 30 times a second. So that's the Crab pulsar. This is also called M1, if you're into the M numbers. Now, this is an important idea I wanted to show you right off the bat here. We basically think about star life cycles in terms of 2 types of stars. The big ones, the ones above 8 solar masses, and the small ones, or at least the average ones. That includes the small ones like the sun. And we'll take the small ones first. Stars like the sun run out of hydrogen and then run out of helium, and then they become a red giant. They'll grow to sometimes 100 times their current radius. And then they need to get under the Chandrasekhar limit, which is 1.4 times the mass of the sun. And to do that, they throw off gas and material that is called a planetary nebula. And I apologize for that name, friends, but that was given to these objects in the 19th century when people didn't know what they were and said, hey, that looks like a planet. So they called them planetary nebula. It has nothing to do with planets, just remember that. This is just material thrown off as a star tries to get down to become a white dwarf. And a white dwarf, we've talked about, as an object that isn't burning anything. They're usually below 1.4 solar masses, and they're about Earth-sized objects with densities about 1 million times of water. So that's a bizarre object. But they basically just cool off. Now, the same cloud which gives birth to average stars also occasionally gives birth to massive stars, and these are stars either 8 solar masses or above, up to 40, and sometimes even beyond that. These things go through several nuclear burning stages. Okay, and I'm going to show you that in 2 seconds. And when they do run out of nuclear material, what happens is they turn into a red supergiant just before they're getting ready to explode in a supernova. Remember, the smaller stars do not go supernova. It's only the big ones above 8 solar masses that can. Here's your supernova thing. And you get two results from this. You get either a neutron star or you get a black hole coming from the supernova. But the other thing about this that I'm going to emphasize in it shortly is that a supernova itself doesn't just produce these things. It produces a lot of heavy elements that are thrown into space that are absolutely essential for the creation of Earth-like planets and for the development of complex life forms. Now, here it is, friends, the important idea about what supernovas do. You need to know this stuff. Supernovas are some of the most important objects in the entire universe. They, number one, they release heavy elements, and these heavy elements are the elements from helium to iron in the periodic table that were created during its red supergiant phase. So and I'm going to show you the details of that here in the next few charts. They create these elements, and then when the star blows up, these elements are thrown out. And this is really the stuff of which Earth-like planets are made, and the stuff of which complex life forms like you and me could not exist without: carbon, oxygen, nitrogen, etc. And so without that, you don't have complex life forms. Second thing they do is during the blast itself, which is humongous, supernova blasts are incredible, they create what are called super heavy elements, and these are the elements heavier than iron. An example of these is uranium, which is a radioactive element that spontaneously gives off heat. And uranium plays a key role in heating the upper layers of the Earth. And also, gold is one of the other ones that's produced. So all of your gold jewelry wouldn't exist, and your cell phones that use silver wouldn't exist without supernova blasts pumping out these super heavy elements. Now, the shock wave, due to the blast, there's a big shock wave because this is an enormous explosion. If it hits a molecular cloud, that's one of the clouds that may collapse into a star. Just by the virtue of the fact that it hits it, the shock wave can trigger the collapse of this cloud. And while it triggers the collapse, it also seeds the clouds with the heavy elements that I was talking about earlier, needed for Earth-like planets and complex forms of life. That's it, friends. That's all they do. Those are three of the most important things that occur in the entire universe. And in the history of the universe, see, the nice thing about supernovas is they pop off generally at less than 10 million years. That's all it takes to go from a baby star to a supernova blowing all these heavy elements all over the galaxy. And so you can have several generations of supernova explosions and really pump up the abundance of heavy elements and trigger the birth of many stars. And that's why it doesn't take long to outfit the galaxy for Earth-like planets and complex life. Now, this is just to show you, this is not one of the greatest HR diagrams I've ever seen, but notice here we have the temperatures going to the left, increasing to the left. Here we have the luminosity in solar luminosities, 1, 2, 3, 4, 5. So this would be 100,000 solar luminosities. Now the big stars over here are simply, when they run out of nuclear fuels, they move to the right here and bounce around back in here for a while until they finally get to silicon, which is the last thing that burns. And that eventually triggers the supernova, and then they disappear from the diagram. You can see even the sun here, way down here, which is not a giant star, when it runs out of hydrogen, it goes into a red giant stage where the outer layers are actually pumped up, because what happens is the core collapses. When the sun runs out of hydrogen in its core, there's nothing to support the weight of the core. So the core collapses, that produces a red giant stage. And then eventually helium is ignited, but helium doesn't burn until 100 million degrees. That's a lot more than 10 million for hydrogen. And so it'll burn for a short time, and then you'll have another core collapse and go through another red giant phase. Now, here's the details of the evolution of big stars that become supernovas. Notice that at the very center, we wind up with what's called iron ash, and that's caused by silicon fusion. Let me get to there in a second. But out here in the outer layers, We actually have hydrogen fusion going on. We have helium fusion going along. This is actually the sequence that even small stars burn at, hydrogen helium fusion. But notice the big stars can burn almost anything except, as you'll see, iron. Carbon is the next one that fuses at very high temperatures. That's around 400 million degrees. Then oxygen fuses, neon fuses, and it goes all the way up to silicon. There are lots of smaller reactions that are not shown here. Basically, you should think of these stars as basically creating all of the elements that are now seen in the periodic table of elements that chemists love so much. And this is the way that the universe does it, apparently. Now, here's the exciting part. The last thing that burns is silicon, and it burns way down in the center of this object because silicon only burns at about 2.5 billion with a B degrees. So it's an immensely high temperature. And 2.5 billion, I mean, the center of the sun is only 16 million. Okay, so that would be a cool breeze compared to what's going on in the center of these supermassive stars. So the silicon pumps out some iron at 2.5 billion degrees, and this happens quickly, as you'll see in the next slide. But what happens is that iron won't burn. So the nuclear physics of the universe is set up in such a way that no matter what the temperature is, iron will say, no, thank you. It will not burn. So when you produce the iron, it's like throwing a bunch of ice cubes in the middle of this star. The central temperature takes a dive. The whole star gets destabilized. And the outer layers, which have these, this is a star of at least 20 solar masses. The gravity is so strong, it destabilizes the entire star, not just the core. And so it begins a collapse. And that's the trigger for the supernova. Here's this is to give you some idea of times for these various reactions I was talking about. In a star this big, 25 solar masses, it only takes 7 million years to burn off all the hydrogen. Remember, this thing has 25 times the hydrogen that the sun does, and it burns it in 7 million years compared to 10 billion years for a smaller star like the sun. Helium goes to carbon in 700,000. Carbon goes to oxygen in 600 years. The oxygen burns to silicon in 6 months, and the silicon is burning at 2.5 billion degrees, so it only takes 1 day to burn out all the silicon in an object this humongous, which is unthinkably big. The core collapse, due to the fact that the iron won't burn, it's like putting ice cubes at the center of the star. It completely destabilizes the star, and the whole star collapses in about a quarter of a second. So this is an incredible event. When the star collapses, of course, there's two things that can happen. It can form a neutron star composed of a core of neutrons that will stop the collapse and cause it to reverse because there are going to be neutrinos and other things that are actually, it isn't just a rebound. These whole outer layers of the star are blown away from the center of the supernova. That's what a supernova explosion is. The other thing that can happen is if the mass is above 25 solar masses to begin with, the star's gravity will be so strong that it destroys the neutron core and literally punches through space-time and forms a black hole, which we'll talk about next time. Okay, this is an important topic. I wanted to show you the ages of star clusters. Here we have 1, 2, 3, 4, 5 HR diagrams, and they're showing you sort of time action here. And here's times 0, here's times 10 million years, here's 100 million years, here's 1 billion years, and here's 10 billion years. Okay. And so when the thing forms, this is what the HR diagram looks like. This is for a star cluster. This could be hundreds to hundreds of thousands of stars, depending on what kind of star cluster it is. And so the thing about star clusters is they're all born at the same time, all the stars in the cluster are, and they all have the same or similar composition. So there's only one difference between the stars in a star cluster, and that's their mass. Their masses are different, okay? So when you have a whole bunch of stars forming at once, the small ones, remember, take longer to get to the main sequence than the big ones. So the big ones, notice, are already here, and the small ones haven't yet reached the main sequence. That's normal. That's what we'd expect. Now, in 10 million years, See the arrows up here? Remember, these are the massive stars, these are the small stars. In 10 million years, some of the smallest stars, this is probably about the sun right here, because the sun takes almost this amount of time to get to the main sequence. But some of the smaller ones still haven't gotten there. But some of the big ones, the O stars, have already burned through all the stages of nuclear burning I just showed you. They do it in less than 10 million years. And guess what? They're headed out to the right of the HR diagram, like I showed you before, to their rendezvous with destiny, which means they're going to go supernova. Now, and then they disappear from the diagram. Now, 100 million years later, everybody almost has finally gotten to the main sequence in this low mass category. All the red dwarfs are there. But notice all these big stars have already left because they've already burned through their nuclear fuels very quickly. And we have what's called the main sequence turnoff. That means that these are the most massive stars right here that are still on the main sequence. All the more massive ones up here have already gone. So the main sequence turnoff actually tells you the age of the cluster. That's what's so interesting about this, because if it's 100 million years, we know exactly what the mass of the stars has to be to burn through all their nuclear fuels in 100 billion years. And it's right here, and these guys are already becoming red supergiants and so forth. Now let's go up to 1 billion years. Remember, how long does it take the sun to burn through its hydrogen and helium? About 10 billion years to leave the main sequence. But what you're seeing is that the main sequence turnoff actually moves down the main sequence. And so the next stage, notice it's way down here. There used to be stars up here when this cluster was young, but they're gone. And so it's like a candle. It continues to burn down the candle. And finally, 10 billion years, here's the main sequence turnoff. And guess who's getting ready to leave the main sequence in 10 billion years after birth? The SUN, which rhymes with the sun, which rhymes with fun. And so by looking at the position of the turnoff from the main sequence, we can actually measure the age of any cluster. Powerful idea. Check that out in the text to talk about it more. Now we're almost done. Here's the discussion about the low mass main sequence stars. We've talked about how the big ones blow up, but red dwarfs are the ones. These are actually main sequence stars, but they have temperatures barely above 10 million because they're so small. Their masses go from 0.08 to 0.4 solar masses. They're totally convective. Remember, the outer layer of the sun is the only thing that's convecting in the sun, but these guys are totally convective. For that reason, they can never become red giants. Their lifetime can be into the trillions of years. And the point I made before is that none of these guys have ever died, because even the red dwarfs created at the beginning of the universe are nowhere near yet running out of their hydrogen. So it's an interesting situation. Sun-like stars from 0.4 to 4 solar masses cannot burn carbon. They're too small. The sun cannot crush its core to temperatures around 400 million degrees. So helium is the last thing they can burn at 100 million. Sun becomes a red giant twice. And the final state is a white dwarf. I mentioned that to you before. Remember, white dwarfs are objects that are not burning anything. Now, planetary nebulas have nothing to do with planets. Make a note. The mass, this is simply mass that's thrown off late in the star's life. And these guys are going on big diets. They try to get down to 1.4 solar masses at least, so they can become white dwarfs. By the way, if you have a white dwarf with a mass greater than 1.4 solar masses, what happens is that the electrons in the white dwarf, which are basically supporting the weight of the whole star, get crushed out of existence, and they get crushed into neutrons, and you have a big explosion. And so that's why white dwarfs can't be bigger than 1.4, because they aren't stable. White dwarf doesn't burn anything. Degenerate matter, that means it's in a closest packed situation that can't be any closer. It'll destroy the star. The density is about 1 million times that of water. The Chandrasekhar limit, but named after a famous astronomer originally from India, who got the Nobel Prize in physics for this work, by the way. White dwarf has to be less than 1.4 solar masses. So there's the rundown about